I think we can start now. Third day of the workshop, and today in the morning session we have a few talks about the machine learning and also the bispectrum, and we will have five talks in the morning sessions. And the first speaker is Professor Utpal Garai, and Professor Gora is currently professor at the Computer Vision and Pattern Recognition Unit, ISI Kolkata, and also he's the coordinator of the Center for Artificial Intelligence and Machine Learning. And his main research area are the AI system, machine learning, and deep learning algorithms. Uh, he did his bachelor's and master's from the computer science and engineering from Jadavpur University, Kolkata, and PhD from ISI. And he received few awards, that CNRS postdoctoral fellowship in France, also JSPS fellowship. There are few awards he received, and today he will be talking about the advance in machine learning and their application in cosmology. So, Professor Goy, now
Thank
it's
you. Thank you. So, very good morning, everyone. Uh, this is the talk outline today, but probably I will prefer to discuss with you more if you are interested to apply machine learning techniques for your work. And since I am not from this field, so but I'll try to present some of the problems. I mean, ongoing computational problems in cosmology. But if required, probably I can ask you the meaning of certain terminologies. But before I go into that part, I'll start with some machine learning basics. But I'm sure that all of you, I mean, who are in this room, you know about these things. But very quickly, I'll go through the concept, and then I'll talk about the advances that has taken place in last 10 years mostly. Though these are, I mean, conceptually they are not very new. I mean, convolutional neural network or RNN, but I mean the success stories are quite new, maybe last 10 years. So idea of CNN, convolutional neural network, what is convolution and pooling, then what is activation function in terms of neural network, uh, then these CNNs, I mean the most popular CNNs which are nowadays in use. And after that, I'll talk about one more new architecture. This is called recurrent models. And then faster RCNN, and then GAN is for generative adversarial network. But briefly, I will. So my goal is to show you that the power of this network, what they can do, so that you can relate with your work. That okay, you have a similar problem. Can you try this kind of network or this kind of machine learning algorithm? And then I'll talk about three problems in cosmology. These are kind of ongoing problems right now. But okay, so till this point, for certain problems, you will show that okay, deep learning. I mean, these networks are doing very well, but there are issues, and that's why I will talk about certain points, not only explainability, but uncertainty management. What is the confidence when you use this kind of network, etc., etc. So let's start with this machine learning basics. So mostly, so machine learning, it's not a very new term, right? So if you look at, I mean, most of the algorithms, I mean, basically they have basis in statistics, and so I can remember, let's say, end 90s, and also next another couple of years, we used to tell pattern recognition. And then suddenly I found that machine learning, this particular term is becoming more popular. And nowadays, hardly people talk about pattern recognition. And then gradually we are talking about deep learning, and in general sense, we talk about AI, I do AI kind of thing. And AI also is very old term. I mean, in 1950s, mid of 50s, this term was introduced. But yeah, so I mean, irrespective of these terminologies, because a good amount of business is associated with this. I mean, machine learning, pattern recognition, AI, all these things. But you see that what do you want to do? So one task is prediction. That so we want to predict. Uh, 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 a class of problems are basically prediction problems. So there we use regression kind of algorithms, and then uh, certain problems are clustering problems. What is clustering? Say you have data, you want to group similar data together, right? So this is the clustering problem. So many problems are basically you can view them as a clustering problem. So you have something, you want to say you get a data set, now you want to group similar objects, similar entities together. So this is a clustering problem, right? And third class of problem. Okay, so clustering problem is also, I mean, sometimes I'll show you, sometimes even in your field also, you have segmentation problem, right? So you get something, you want to segment this into different regions, so you can view that problem also as a clustering problem. And third problem is classification problem, or we call it, say, we want to recognize something, right? Say, then that they say in this is object, so this is a star, right? Or this is something else. So this is a classification problem. That given an image, you want to classify that what kind of object it is, right? Now, so uh, let's say these shows you the linear regression problem, right? So regression problem, and then this graph is showing you the clustering problem. So we have got three clusters here, and this is classification problem, right? So and in fact this is I'm showing you very simple things in 2D, but the idea is basically essentially same. Now, so undergoing what we are trying to do, let's consider this regression problem, right? What do we want to do? We want to predict the value of y from a given, say, input, let's say x. X could be something, right? So, unless and until we know that y is a function of x, is very difficult to predict, right? How can you predict y unless until you know that y is a function of x? Now, so and this is the problem, right? That we do not know that what function it is. That's why we try to uh, approximate this from data, and data is x, right? And we call so mostly other than clustering, you see that this is we these two terms we use very often, that supervised machine learning and unsupervised. Supervised machine learning is where we know the level, right? We know y. So for given x, we know y, that this is galaxy. So you have a say feature matrix for galaxy, and you know this is galaxy, right? You know this is something star or something, right? Now, okay, so we do not know this function. So what we can do? We can predict y from given x, right? So here, say uh, so, say let's say even let's consider simple straight line, right? So y is equal to mx plus c, right? So you predict y. So to predict y, what do you need to know? Just two things, m and c, right? So here you see that this wy we need to know to predict y, and then how do you know wy? So that's why the technique we follow, that okay, we have this data set, we have this data set. So how can we know the right wi, so that finally we want to minimize error, right? We want to minimize error. So what is the definition of error? Let's say we have okay, this function and this function not same, sorry. So we can compute y bar. You know this is the right y, so the difference is giving you the error, right? And then this error we want to minimize with respect to what? With respect to this w. So this is the main challenge here, that how to know the weight vectors or wy, so that my prediction quality will be very high, right? Now, what is the way? So there are many ways, but this stands. So you see that here also we engineers, we assume many things. I mean, you mathematicians and physicists can uh, that can surprise you, that how do you know that this loss function is convex? We assume. Otherwise, you see what happens, that the gradient descent algorithm you won't be able to apply, right? So this entire computation, how to learn Wi, we assume that this is the nature of the loss function, and then we apply gradient descent to and we assume that this is the global minima. And so now you can have again a question, how do you know that this is the global minima? Because using this algorithm, there is a chance that you will be stuck at the local minima, and there is no way to get rid of that, right? So in practice, what do? We run this kind of algorithm. Let's say for my language learning problems, I run 300 times, assuming that at least, and that happens. I mean, let's say 3 times I did not stuck at a local minimum, right? Kind of this kind of approach we follow. So this is, I mean, uh, true for regression, true for classification also. You can have many different classifiers. Some of the classifiers are decision tree kind of thing, right? That you know the feature, so you can have binary decision tree, that is that feature is there, yes or no, and gradually you generate the binary tree to get at the leaf nodes. Now, so if you think about any machine learning task, uh, including the some of the tasks I'll talk about which are there in cosmology, you see the major steps are like this. So first we have to think about that what is the input, right? Is it image or signal or video or whatever? I mean, input is available in what form? Now next is, how can I represent that input in terms of feature? Because now, so in statistics we talk about random variables, right? So in other domains we talk about aspects, attributes, whatever. But what do we need? That let's say I give you an image, right? So what will you extract from that image so that you will have X? Because X cannot be the entire image, right? So what kind of feature? So feature engineering is very important, that feature representation. And after that, whatever you do, I mean, you get the definition of X and then use that X for regression, clustering, classification, whatever. Now, the good amount of research in machine learning is related to feature representation, that how to represent your input into X in form of X, so that you get input. So there are many, I mean, research related to feature extraction, feature selection. So what is feature selection and extraction? Say, let's say you extract that, okay, feature is weight and height, right? And but the feature selection, and I think you are aware of this. Say you select 100 features or 1000 features, right? The moment you run PCA kind of algorithm, right, for dimensionality reduction, the kind of features you get is called feature extraction, because you do not know the meaning of those features. Say I start with height and weight, I know the meaning of height, the feature height, weight, but the moment I run PCA, I can get something, the meaning of that feature I do not know, right? So that is feature extraction. But anyway, this terminology, basically they come from pattern recognition textbooks. And then we talk about dimensionality reduction, where we deal with large number of attributes. Okay. Now, this was going on for many years in name of pattern recognition and machine learning. But the community understood that the major bottleneck here is the availability of the domain knowledge, right? So, for example, you give me cosmology data, I do not know anything. I work with doctors or biologists, I don't know anything about their data. So, unless and until somebody from that domain expert explains me that, see, what is this data, then probably I can think about some feature extraction, right? And there are two problems. So, one problem is that unless and until I get domain expertise, I am not able to convert input into X. Unless until I get X, I mean, rest of the things I can have many classifiers, different clustering algorithms, I am not able to run anything, right? So the community started thinking, is it possible to employ machine, that machine will bring that X, right? So, this is one question. Now, uh, getting answer to that question has, I mean, two implications. One thing is that, okay, so dependence on domain experts will be less, that is fine. And second thing is very crucial, that the community argued that time, that okay, the knowledge you are getting from the domain experts is fine. That helps you to convert input into X. But who tells you that is the right knowledge to convert X into, I mean, input into X? So, this is another crucial thing. Who tells you that this doctor is the right one to give you the definition of this disease, right? So, because I mean, human ability has some limitation. Now, can we employ machine to go through, say, I mean, millions of data and find out what feature will be right to execute something, I mean, to get a decision, to execute something which is in our hand, right? So, from this perspective, actually, we entered into a new era of computation called deep learning. So, from machine learning to deep learning, the difference is this, that we employ machine to find out right features, right, to execute something, to execute a task in hand, right. Now, so this is the difference. So, for example, in the era of machine learning, if you ask me that design a face recognition system, I will ask you, probably the forensic experts, that how do you define face? So, they will tell me certain features and this, and I will convert a face image into X following that knowledge. But following deep learning, I don't need anything. I just need, say, millions of images and annotation, right? So, I mean, it's not very difficult to follow. Let's say the way we teach children the how to recognize letters. Our traditional way, that this is a, these straight lines, two slant straight lines joined in the middle by another straight line, right? You give the description of each letter, that this is A, this is B, this is C, right? B is a vertical line and then cup shape, this thing, this is fine. Now, instead of doing that, if you do that, see, you don't tell anything, you say this is A, this is B, this is C, and you do it thousands times, right, randomly. This is A, this is B, this is P, this is K, right that. You are not giving any definition that what is A, what is B, what is K. And this policy also that will work. You are sure about that, right? Now, you see the difference between these two policies. So, for the first policy, we can say define this as if we have a grammar, we have a knowledge base, we have a rule base, right? And that's why the data requirement will be less. But in absence of that grammar, in absence of that knowledge base, we can follow the second approach, provided we have a source of, I mean, a huge data set, right? Now, this, this is kind of machine learning and deep learning. You tell your child that how to recognize A, that is machine learning. You are giving the feature set, definition of features, right? And the second way is deep learning. And so, in deep learning, though most of the algorithms are quite old, so three things actually contributed heavily. The availability of big data, right? So, because of the internet and then sensors, we have developed huge amount of data that is well connected to cloud, internet, etc. And second thing is that computational resources. So, to deal with this huge amount of data was not that easy unless and until we had that enormous computational power that we got in last 1 decade or 15 years. And third thing is that algorithmic, some new algorithms, right? Though CNN and etc. old, but I mean some modification came in last 10, 15 years. So, these three things contributed positively. That's why this is possible. So, academically, this is the, I think the first one. It's not a commercial success, came later. So, this community, they did a ImageNet challenge. Earlier in our machine learning community, our challenge was like this: 10 class problem, 100 class problem, like that. But this community first tried to design a human vision like system where enormous number of objects the human vision can recognize, like that, right? Now, so number of objects was around 20,000 categories. So it's not just 1,000, even 20,000 categories, like human vision system. The kind of objects we can recognize a few thousands, right? Now, question is that human vision can do. Probably human vision has seen enormous number of objects, right? It's not that few hundred objects we see. So that's why they created a data set, 14 million images, and then they got a success rate of say 75% initially, but that is kind of a path-breaking results in machine learning, that this is possible. This using annotation of huge data set and algorithms like say AlexNet is basically a convolutional neural network. But I'm not showing you other structures. Another one I should show you. This involves machine perception. So that happened in 2010. Now 2015, this image caption generation reported. There you see that task was, I will give an image to the machine, and machine will give a caption for that image. And for certain captions, I mean the kind of accuracy or the perception ability machine achieved is enormous. So, look at this image, a person riding a motorcycle on a dirt road. So, this much details machine can capture from the image to convert into text. I mean, machine is giving you a text, right? So, that's a very good proof that machine, the understanding ability machine has achieved. Now, very briefly, I will talk about convolutional neural network to show you that how is it possible, this unmanned feature extraction, right? I mean, now without involving human experts. So let's consider this is an image, right? And then the kind of filter we use to extract this. Let's say we use 3x3 filter. So I mean, around 5 we place the filter, and then this is point-wise. I mean, multiplication and overall summation. If you get, you will get -5 like that. So this is convolution, right? So follow it. I mean, I place it over there, and then 3 into 1, 1 into 1, and 2 into 1, right? So 3, 1, 2, and then say this is 1 in. So all these are -1, and finally you get -5 for this position. So this is basically convolution operation. I mean, if you are not able to follow this, just it will take 5 minutes. I mean, on paper, I'll explain you later. But previously, what we used to do, let's say whenever you give me an image, we used to try to extract different features from the image. So for example, let's say this is the filter I designed to extract vertical edges, right? This is the filter I designed to extract horizontal edges, like that. And that's why in the literature there are many filters like Sobel filters, SAR filters, etc. Now, with deep learning, this concept is gone. How? So, deep learning, let's say I will use 100 such filters, right, 3x3 with random initialization of the weights. Because how do I know that these vertical filters or horizontal filters or SAR filters or Sobel filters will help, right? Let machine understand, let machine explore that what would be the right weights or right kind of filters to achieve a task with a very high accuracy, right? So the task will be integrated with this feature extraction. So this actually happened here. You see that let's say right. Let's say this is object recognition, right? Now this is the image, and then low level feature. So let's consider the first level where you are using 3x3 filter, right? So basically we are considering very low level features. The moment in the second level you use 3x3 filters, actually you are considering 9x9, right? So gradually we say high level features we extract, and finally the trainable classifier this classifier will classify this is car or this is tree or this is human, like that. Now you see this entire thing is integrated now. So training will be end to end, right? So uh, so unless and until you set the right weights in the filter, your classification accuracy will be hampered, right? So following this, now very important is that activation function, because now in neural networks what happens, a neuron receives input, right? So let's say the neuron structure, so let's say this neuron receives input from the different say previous layers, and then output, how will you generate output? So output is, now if it is a linear combination of the input, basically we will talk about linear regression, right? So if it is W1 x1 plus W2 x2 plus W3 x3, we will talk about basically linear regression. But to bring that non-linearity, so we use sigmoid kind of function. So if x is this, then the activation function is a sigmoid. Problem with this, now this is the derivative of sigmoid, right? Now if you have a very deep network, so these derivatives will, and you know that training will be following gradient descent, right? So let's say it is x cube, the derivative will be x square. Then again you take the derivative x, then 1, and then it vanishes, right? So this is a big problem in deep neural network. That this problem is known as vanishing gradient, because we deal with huge, deep architecture. So now as a result, what will happen? You will find that only last few layers they learn something, but other layers are not learning anything, because the gradient is not propagated. The gradient has vanished, right? So there are again some research to how to get rid of this. So instead of, so this is another activation function. So this is defined as max of x0. So at least this is the problem, that at x is equal to 0, this function is not derivable, right? So if it is not 0, then at least you can pass x, and then derivative will be 1, right? At least some derivative will flow. This is another, for classification, this submax. So these are the scores, say finally you get from different neurons, and you to convert them into probability distribution. So this kind of, just we use a denominator, summation of the denominator to make these numbers into probability scores, so that taking decision is easier. Now this recurrent model, now with neural network model, the problem is you show something and network will take a decision, right? Now this feed-forward neural network doesn't have this ability that what I have seen before, because nowhere you capture this knowledge. You show me car, the network tells you car. Then you show say image of tree, the network tells you tree. But there is no way to capture the knowledge that what I have seen before, right? So that's why in time series kind of data, even for language, right? Because the word I utter, the kind of word I choose, that has a very high dependence on the words I have used before, right? Similarly, in time series data, say today the kind of say share value you see for a particular company, that has a dependence on many previous steps, right? But so that's why this kind of neural network came, where so this is the series, and you see now the the decision we take at this stage is going to the next stage, right? Now the obvious question came that how far the network should remember. That becomes another research problem. That okay, you are giving me say for example weather forecasting. How far should you remember to predict tomorrow's weather? That becomes a problem, right? So another network came called long short term memory. It is popularly known as LSTM. That solves the problem that inside the network there must be a forget gate that will control that how much the network should remember, and rest of the things network can forget, right? And then another problem came. So, I'm sorry, I mean, don't follow Bengali script. For machine translation, say the another problem came that okay, things are not that. So, even for any machine translation, right, from English to Hindi, not that it is word by word translation, right? Then I mean the translated sentence will not mean you anything. So, how to put attention that which part will be translated to what? It is not that okay, say tomorrow's weather is this, day after tomorrow is this, day after then after that this is not like stepwise decision. So a new kind of network came. It's called attention model. That whenever you are decoding something, your architecture will tell you that to decode this, you put attention here, right? So, for example, for face recognition, to decide that this face is for Utpal, the network will learn that to decide that this is Utpal, these are the parts where network should put attention, right? So, network try to again. So, I mean, uh, it is easier said than done. So, claim is slightly exaggerated. I will show you later on that for we have engineering success, but foundation is not that strong. And this faster RCNN, basically regional purpose, this kind of CNN, it is a very good network for object labeling, that this is object, finding the object bounding box as well as classification. And for your many of your problems, basically this RCNN kind of network will be very useful. That's why I added this. See that this is the image, and then so this is an object. So first thing, it can identify that these are the objects, and then it can recognize the kind of objects. Okay, and lastly, this generative adversarial network is very useful for generating simulated data, and in cosmology, since simulation is a big problem, so this GAN kind of networks can help you a lot. So, the essentially what it does, the very nice idea this network makes use of. Let us say you have a real data sample, right, but you know that you do not have real samples in many, just handful of real samples you have. Now, based on that, you want to generate many simulated samples, right. So, first you start with a say latent random variables, or even you can start with a zero image, just completely noise, right. And then generator will give this the discriminator, the task of the discriminator to tell you no, this fake image, then discriminator wins, right. So, the moment discriminator wins, what do you want to do? You change the parameters so that your generator can generate a better quality image. So, idea is you start with a very bad fake image, and then gradually you are converting it to a very real image, so that discriminator will be full. So, the task of this network is to fool the discriminator. The moment discriminator is full, you know that you have generated a nice real looking image, right. So, that is why GAN is I mean is a very popular network in generating simulated data set. Now, with this foundation, quickly I will go through 3 problems, because I am not from your field, but where people are using. So, this work is from it's a big group, Stanford, UC Berkeley, and some other universities. So, they have used GAN, I mean generative adversarial network, to generate a very high quality resolution image from low resolution image, because needless to say that in your field, problem is a small area you have very high resolution images, right. But for a large volume of universe, you have very low resolution image, right. So, this is the problem you face. So, what they tried to do, okay, we have low resolution image, can we use GAN to generate high resolution image from that low resolution image? And you see the evaluation. So, this middle one, the high resolution image, is basically they had as ground truth, right? Now machine has generated this right side image from left side image, and then they compare that how much success machine got to generate this one. And this is a, I mean, they published it in last year, Proceedings of National Academy of Sciences. So this is a very notable success where simulation task you can make, you can use different neural networks to generate images. Then SK, so I was discussing with Supratik. So this is a one software data challenge one SK. They call it SDC, software data challenge one under SKA. So data is available, very nicely organized competition. So they provided 9 images, three at 3 frequencies, and for each frequency at 3 different depths. So altogether 9 images they could give, but they defined many different tasks. For example, I'll show you the task. Potentially the challenging aspect, that number of sources these images contains is huge, 30,000. I mean, if you look at the paper, you will see that data details. So it's not possible to find out the sources manually from an image. So it has to be automated. One thing. Second thing, that image sizes are also huge. I mean, it's not possible I fit image into my computer and I can take some decision. And even how to use machine learning on these images is another challenge. It's not very trivial. Then along with this data, because this is only nine images, right? So the moment you decide that I will use some learning algorithm, it's not, I mean, where is data to learn, right? So they provided some simulated data also. A catalog revealing only a fraction of the simulated galaxies was released for each frequency band. So the basically major idea was to test and debug your procedure and providing a training set for methods requiring training. So you train from this data, and then you do the task on these real images, and you see that what is the performance. So several tasks, actually 8 teams participated, and the deadline was 2019. I think after that SDC2 was there or not, I am not sure. I didn't follow. So 3 teams basically out of these 8, they use neural networks for achieving different tasks. Now, task were, say for example, source coordinates in terms of RA and DEC to locate the centroid, where appropriate the core positions, and number of sources, counting, and then integrated primary. So all these things, I mean, for many tasks, I could not understand the meaning of the task because it's from your field. Evaluation results demonstrate that this is very, very important observation, but mind it, note it, that observation 3 years before. That evaluation results demonstrate that the importance of building domain knowledge and expertise on this kind of analysis to obtain the best performance. So if you look at the leaderboard, top 3 positions are basically using physics models. So deep neural network got 4th position, but that happened on 2019. Now, this year, February, this work already is reported, a deep learning framework on the same data set, but this team did not participate in the competition. I was going through that what was the status of that team, but they didn't participate. But they reported these results, and they showed that they could outperform all the results. I mean, which was reported in 2019, right? So using this, and for all the images, 9 images, they got enormous improvement, 25% to 200% improvement. Okay. Now you see, this is one sample results, and this is for the detected sources with their bounding boxes. But this kind of task you can achieve using faster RCNN kind of network, that source localization, object localization. But I'm sure that not enough handshaking is happening between these 2 communities. That's why this kind of network is not yet tried on this. I mean, machine learning community and cosmology community. Now, finally, So, this is another uh, nice work, but it's quite old, 2017. What they did, so they took the 21 centimeter signal data, they involved neural network, but again, I mean, neural network in the school of machine learning kind of thing. I mean, they provided human crafted features, right? But the goal was to estimate these three key parameters: the ionizing efficiency, the minimum virial temperature, the mean free path of this, right? So, they configured a neural network. So, data was, they created 70 training data sets from 21 centimeter power spectrum, and they basically they use quantization technique to convert the data into 14 bins. So, input is 14 dimensional feature vector, right? And then output is the corresponding EOR parameters, these three basically they, so output you will have three new nodes, right, to estimate the three values for these three parameters. Then they compared the results with 21 CMMC. Basically, they used MCMC kind of simulation and 10 to the power 5 number of realizations of the power spectrum. So, what they claim that using just 70 training data sets, they could achieve the kind of accuracy they achieve is very similar to this traditional approach that use MCMC kind of simulation with huge number of data points. So, obviously, the second one, I mean the earlier one was quite slow, uh, and these very similar results they achieved with neural network using 70 data sets. So, obviously, they said that with more training data probably they could achieve better accuracy, right. So, they reported in 2017, just starting from that point you can see that what are the other works already reported later on. So, with this I think this I should show you, just I will take 2 more minutes, right. So, so far normally you will be amazed with the power of deep neural network that okay, and that is why happening industry 4.0 is completely based on new I mean discoveries in machine learning. But now if I show you certain things that will dishearten you, but anyway engineering success you cannot I mean ignore, right. That is why yesterday I was discussing with Girish that okay fine, using this kind of techniques is not easy to study physics, but it's good to see that okay this much accuracy machine can achieve, right. What doctors are basically using today is the kind of AI techniques not to replace their skill, right, just to get some assistance that okay machine can tell that oh this is the AF problem from ECG, where it's very difficult for a human doctor to tell that this is AF problem from this ECG. So, how can machine do this, right? Now, you see that this is from a, this result is from a very good object recognizer, where panda is recognized nicely as panda, but the moment you add this adversarial noise to this image, and I call it adversarial and imperceptible noise, because to human vision panda remains panda, but to machine vision it becomes G1, and you see the confidence of the machine, 99.3% confidence of the machine, that machine says no, it's G1. So, we designed certain, we call it adversarial attack, certain example. Now, you see that for all these images machine was perfectly right, but now the moment you add these imperceptible noises, for every object machine is telling them ostrich, for every object. So, you can configure, so this is called white box attack. So, the idea is you go on changing the pixel in the input unless you fool the machine, right, and nothing you do. But after the machine is fooled, you see the input images, I mean never human vision will be fooled, right. So, this is, be careful about these things. These shows, I mean I can show you many other examples from language domain, vision domain to tell you that even we are getting enormous engineering success, the reasoning ability of these kind of systems is very, very poor. I mean, So that's why the kind of research, I mean, if you follow the research in AI and deep learning, explainability is a big thing, that interpretation. And also, so far what we are trying to do, we are trying to learn the correlation. You are giving me X corresponding Y, and I am trying to understand the correlation only, right? But correlation is not the only thing we should look for. We should go for causal analysis, but very tough. It's not that easy. So maybe it's a very new research, that causal analysis for AI system. Now there also, who will give you the causal graph, right? So this is another problem. Otherwise, if you know the story, right? So if you plot that amount of chocolate consumption in a country and the number of Nobel Prizes won by that country, if you plot them, you will get a very high correlation. And if your country decides, oh, increase the amount of chocolate consumption to get more Nobels. So that is actually happening sometimes here, because the causal analysis is not happening. At the same time, certain things like, uh, can I measure confidence of a classifier, right? Say, what is the uncertainty of this system? So all these things, so most of the things are coming from engineering field, right? And here we are not that strong, that how to measure confidence of a system, how to measure uncertainty. So that's why I think, I mean, physics brains, if they come, many of the problems will be solved, because you are already well trained to do all these things. Thank you very much.
Thank you, Professor Garain, for nice talk. And now it's time for a few questions. Yeah.
So my question is, even before applying the machine learning technique, if you want to decide the training data set, do you need domain knowledge? Because you might want to balance your training data set so that it cannot be biased when it's interpreting something.
True, but see, in reality, it is very difficult to get a balanced data set, right? But things are not balanced. I mean, if you look for, let's say, any classification problem, right? So always there are some classes which are rare, could be critical. So that will happen, right? So it is nice to have the real representation in the data set also. We can make it balanced for our own, just I can report good accuracy in the paper, right? But real problem won't be solved. So that's why, I mean, can we design new algorithms that can tackle this kind of problems? That rare class, probably existing machine learning algorithms will miss, right? But how to bring them back, because they are critical. Even in medicine field, this is very important. Many of the diseases are rare. You won't get enormous samples, right, in your data set to train machine. Then machine will miss them, right? This is the problem with probability, right? Winners take all. So those diseases, your machine learning algorithm won't be able to identify. So anomaly detection. So these are again communities, because most of the success are from academics, you understand. But the moment these, I mean, industry people, they are trying to apply this algorithm, they identify these things. That say in bank fraud cases, it's not that the thousands of fraud cases they identify, right? So bank fraud cases is anomaly cases, rare cases. So how to identify by machine learning algorithm?
Thank you.
So the result from the machine learning image. So to understand if the result is correct or not, we have to employ a human brain again to see if it is a bicycle or if it is ostrich, let's say. Now the question is in the example of stars where you got a low resolution star and then get high resolution star. So then you don't have the picture of high resolution star. So how you are, I mean, how they?
Oh, no. Okay,
Sure.
so this middle one, they had this data to compare the machine results. So they generated this high resolution from the low resolution using their traditional knowledge. Maybe some physics knowledge they applied to tell. Say for example, I can do this to this, right?
Yes.
Now, how will you understand that what my machine is doing is the right? So you have some set of things with you that you have generated with your physics knowledge, and then now you will compare the machine accuracy. So they had this.
Okay, but in general, if we don't have the high resolution image, and
We don't have, that's the thing.
yeah,
And
yes,
that's
then
why,
how we trust the machine? I mean,
okay, so trust will come from this, that at least I have, let's say 10 examples. For these 10 examples, you see that machine is doing well. Now using that machine, you can generate 100 more examples,
yes,
right? But I mean, manually it's not possible to verify those accuracy of those 100 examples. But again, the question is that, yes, so reliability of this machine, so confidence of this machine. So, I mean, if you can quantify, I mean, that's great. I mean, still it's not there.
thank you. Another question.
So what is the meaning of that?
I mean, say for example, your face remains your face. I mean, human vision is not full. Say for example, here you see, so this is noise, right? This noise is added to this panda image. But after adding this noise, this is the image. I mean, image is not deformed visually, right? But still you see that machine is full.
Okay, but if I tell the machine that I have an estimate of the noise, can I tell the machine that okay, this is the image, but I have an estimate of the noise? So
No.
can the machine separate this? Then again, it can find the panda again. No, I'm saying that
No, the task is like this. Say for example, you have designed a object recognizer, right? Fine. And I have access to your object recognizer. So I know that you claim that my object recognizer can give accuracy, 100% accuracy. So my task, I start with an image, then I go on changing different pixels so that your machine is pulled. Right now, if you say that no, I have a module for noise estimation, etc., then you have to design another model. You give me that model, again I'll try to pull it. So these will go on unless and until you have a reasoning ability, right? So today's deep neural network, they don't have reasoning ability. That's the thing, and reasoning ability will come from expert systems, right? Now this is a very critical problem, how to integrate these two things. You know that in 70s, these rule-based, grammar-based expert systems, they were very popular, but even they failed. The problem is that the generalization ability was not there, right? So you can have a grammar-based cosmology, but you know there is a limitation. You do not know all the rules, right? Now these data-driven approaches are giving us enormous accuracy, but they don't have the reasoning ability. They don't have that grammar sense. Now, how to integrate these two fields together so that I can design a best of these two worlds, that I take the advantage of data driven approaches as well as I can validate that result using a grammar based approach, or still it's an unsolved problem.
Thank you.
Hello. So my question might be a bit naive, but when we are trying to train a neural network, be it any kind of network, how do we decide that our training set is large enough to generate our required accuracies? So I ask this because often, at least from my experience, when we are trying to train a model in cosmology, we are running very expensive simulations.
Right.
So how do we make sure that we are not over expending our resources, but at the same time we have enough data to
In
have a good
fact,
model?
for big data scenario, we are, I mean, more data we generate, better accuracy we get, kind of things, scenario. But and that's why this is another environmental issues, that deep learning systems, the carbon footprint is huge, right? And so there is no, I mean, precise answer to your question that where should I stop, right? But the currently, because of the industry success, more annotated data sets you design, more success, more accuracy you will get more business, etc., etc. But that has a very bad impact on environment, because we are, you know, this GPUs I mean, servers we are using, the carbon footprint is huge. So that's why people are talking about one-shot learning, few-shot learning, like human vision. Do you need so many examples to recognize a thing? not exactly. But I mean, unless and until we have the right knowledge for human vision, is very difficult.
Okay, thank you.
Yeah. Yeah. Right. Oh, confidence is estimated by a softmax. I showed you, this is not GAN, this is a object recognizer. So yeah, so this softmax, let's say you are doing, let's say 100 object classifier, right? So at the output node you will get 100 scores. Then the scores are converted into a probability distribution, and then for that particular given that node you get 99.3% confidence, right? Earlier it was 55. Okay, so certain panda images definitely will be recognized as 99.3% confidence. No, I mean simultaneously, because this is single, I mean multi-class problem, right? You will get only one level. Yeah, it's not multi-level problem. Okay, sure. Yeah, probably we should discuss more to
Also,
find out
you
a
will
group.
be present in the discussion session, so we can continue.
Thank
So
you.
thank you, Professor Goy, for nice talk. It is thanks. Our next